Garth Hitchens. I'm with Rose Point Navigation Systems, and we build devices and software for boats. And I'm here to talk about our experience and some technical details about a project called Nerves. Nerves is an amazing technology, and I'm curious how many of you have used Nerves, just by show of hands. Anybody used Nerves in this audience ever? Cool. Cool. Only my colleague. All right. Well, this is going to be good because I believe this is an amazing thing, and more people need to hear about it. Has anyone seen a talk on Nerves before? Wow. Anybody have a Beaglebone or a Raspberry Pi? Oh, excellent. And what about Arduino? About the same number, but not the same people. Interesting. Okay. So I'm going to go to a bit of a history. This is the very first computer I ever programmed. This was a Sim-1, which was loaned to me by my junior high school math teacher, Mr. Tong. And I was 13 at the time, and he noticed I wasn't really into math, and he said, well, you know, what are you into? And I said, oh, digital electronics is interesting. So he gives me this box, and I take it home. And this is interesting because it was $239. It had a 6502 CPU, and it had lots of I/O, as you can see. And it actually had a cool little keypad and six-digit LCD display, or actually LED display and beeper. I progressed up in the world. A couple of different things I owned. Interesting, I liked 6502s apparently. So I had, that's what it looked like by the time I went off to high school, and or actually by the time I was about to go to college. And then something happened. I got this. Does anybody recognize this? Anybody can place it? Not the obvious reference, Smalltalk, but oh man, I'm feeling old. So this was a monumental issue of Byte magazine in 1981, and it described Smalltalk. And I was probably, I don't know, 16, 17 at the time. And to me, it was like a whole world opened. It's like, here's this discussion of a virtual machine. I'd never heard of a virtual machine before. And it talked about messages being sent to these receivers. And the whole thing just felt so natural and pure. And like, for the first time, I realized I really wanted to be a software engineer. And I think the word that most summed it up, went past that, is beauty. I found beauty in it. And I've found that beauty in a lot of things since then, but rarely in the computer world. Elixir certainly has brought it back. Let's see. So I actually went to University of Washington, mostly to work on this machine. This is a Xerox Star. And the Star never really made it big in the commercial world, but it was very exciting because it ran Smalltalk. And when I got to UW, I learned about prerequisites, and I ended up working on this instead, and was rather disappointed. So this whole digression is mostly to talk about how I've watched the computer industry grow. And most of you have seen some variant of this slide. It takes you from fairly early history of microcomputers up to now. And the key thing to look at this is you can purchase for $20 today probably more computing power than the entire University of Washington campus had back when I went to school there. And it will fit in your pocket, and it'll run on batteries. And there's actually a whole plethora of devices like this that are on the market. Some of you guys have them. And I want to focus on a couple of them, two in particular that I've had experience with. One is the Raspberry Pi, which I think a lot of you probably have used as your introduction to this space. And this one's a Raspberry Pi 2B. It's their latest model. Quad-core, pretty zippy machine, $35. Incredible what you get. The other one I want to focus on is the Beaglebone Black. And the reason I want to focus on that is because for us as a manufacturer, this was an amazing device. What makes this device amazing from a manufacturer's point of view is that it's open source hardware, not just open source software. I can take the entire board design of this, and I can build a product out of it. I can take it and prototype with it, and then once I'm happy with my product, I can go to a board manufacturing house and have them actually build me an exact product using their layout with my board around it. And all the parts are easily sourceable in low quantities, so I can build small quantity devices on it. This is a big deal. It also has a CAN controller built in, which is really important to us in the boating market because boats use a lot of CAN interfaces. I don't know if any of you guys even are familiar with CAN, but it's a controller area network, popular in the automotive industry. So going back to this, you'd think with all this horsepower available that most hobbyists would have picked up these devices and done lots of cool things with them. And they would have built systems that they could ship products around or have done something really incredible with. And if you look at what the hobbyists are doing today, and you say to hobbyists, hey, you know, what are you doing with embedded systems? What you end up getting is usually this. And it's rather sad to realize that what you're getting in CPU power and memory is pretty much, well, CPU power is much better actually, but memory you're getting very similar to what my Sim 1 had back in 1978. And it doesn't have an LED display, and it doesn't have a cassette tape system. But it does have 32K of flash, which, you know, I used to store 64K on my cassette tape, so I'm not totally impressed with that. So this is to really reinforce the point of just how different Arduinos are from things like the Raspberry Pi or the Beaglebone. They're really, really entirely different animals. So how come? Like, how come people haven't more built interesting products with these larger devices? I mean, they do. They build their own little sample things, and they play with them for a while, and then they sit on a shelf, but they don't actually build things that ship in the real world out of that technology very often. And you know, the question, it's like, it turns out that Linux is actually pretty hard to deal with on an embedded device. Most of these devices, like the Raspberry Pi, come with some Debian-based distribution. And Debian-based distributions are really not optimized for devices. They're optimized for servers, and they're optimized for server deployments, and they're optimized for server packaging. So, you know, you've got huge issues because right away, like, you build your thing, you prototype it, you compile your code, you get it all working, and then you go to put it somewhere. And then what do you do with it, right? How do you update it? How do you keep it working well? How do you maintain it? How do you get it to boot quickly? If there's a security hole, how do you fix it? How do you get it to update its packages? Like, all these issues come up, and none of them are particularly clear, especially if the device isn't in front of you. If you want to put it in an application where it's truly an embedded controller, you're not going to, like, stick in with a shell terminal and manage each device independently. So building a real system around these things can be really challenging. Let's see. So this sets a stage for Nerves. And what Nerves is a, did any of you actually see Frank Hunleth's talk on Nerves at ElixirConf, or at the Erlang? Wow, awesome. Then most all this will be new. And I'm going to say up front, I am borrowing some slides from Frank, and I won't go and point out which ones they are since none of you have seen them. So, you know, that's pretty good. But Frank did a great talk on Nerves at both the last Erlang factories in San Francisco. And so you'll be able to spot Frank's slides carefully if you look, because they don't have the word Elixir on them. Because the system, Frank Hunleth, by the way, is the guy who designed the Nerves infrastructure and built it, and runs nervesproject.org. So he's the man. So what is Nerves? So Nerves is basically a framework for building embedded systems in Elixir. So you can tell I wrote this slide. And the reason the word Elixir is there is that I'll get to that later, but basically we've made a decision to embrace Elixir pretty deeply and not try to support the Erlang crowd and the LFE crowd directly. But, you know, they're welcome to use the products. But really we're gearing up and focusing on Elixir as the primary way you do stuff. But fundamentally, it's an infrastructure based on something called Buildroot. And one more show of hands. Anybody used Buildroot before? Wow. So Buildroot is a way to build really small Linux kernels, or Linux distributions, actually, that are kind of baked into a single image. So instead of having, well, something loud going on behind me. Instead of having you know, a packaging system like Debian does, you end up selecting at build time the things that you want to compile in. And it's opt-in rather than opt-out. So you start out with almost nothing. You have to say, oh, I want this version of the kernel. I want this tool chain. I want a tool chain for this processor. and I want to support these chips around the processor, and I want this stuff. And when you make these selections, what pops out the other end is a very small, lean Linux that does exactly what you want. And what Frank did is he took build root, and he took the Erlang VM, and he wrote a shim called Erlinit. And so he got rid of the entire init system in Linux, and basically it boots to Erlang in about, I don't know, anywhere from 3 to 6 seconds, depending on the platform. And then there's some libraries that my company worked on, and those are all in Elixir to try to support embedded systems better. And I'll get to talk about that. And then we've got some tooling. So that's what Nerves is. So Nerves is targeted not at the real-time operating system crowd, right? It's also not targeted at the higher-end crowd. It's targeted in this kind of place right where the Beaglebone is and right where the Raspberry Pi is. And to sort of do a comparison between Nerves and Raspbian, which is the thing that probably you guys are using on your Raspberry Pi, Raspbian's a pretty big Linux distribution. It's got a package manager. It's derived from Debian. It's got all the things you're used to having on the server, but it doesn't boot real fast. It doesn't run on a read-only file system, which is incredibly important in real-world devices. And it also doesn't handle firmware updates very well. So I'll get into some of that. I think the key thing, let's see, is there anything else? Yeah, that's good enough for this one. So the way Nerves work is it takes your app and it builds an OTP release based on your app. Actually, it's using RELX now. No, I'm sorry, EXRM now. And what pops out of that, it then packages up into a root file system that it custom builds a cross-compiled Linux for your target platform, throws it all in a little firmware image, and makes it available to burn. And this is magic. This is really something. This is monumental in the embedded world. It's a little bit tweaky. I was recently at a conference with a British guy, and I learned the term fiddly, which I really, really like. It's a little fiddly, but it does its job. And if you want to customize it, you end up going through menus that look a lot like this, which isn't great. That's the build root menu infrastructure for how you opt into packages. Some of you may, it's same as make menu config for the kernel. And what you end up with this root file system where your OTP release and your cross-compiled ERTS all gets bundled up, and it gets thrown in a root file system that takes about 18 megabytes, uncompressed. And that basically is a pretty significant reduction over any other Linux platform that I've ever worked with. And that fits in an SD card. And the way that we partition things is that we choose a fairly fixed partition layout. In the embedded world, you don't want to have too many partitions because it turns out bootloaders are very tricky. On an embedded systems, bootloaders still use things like FAT12. And so the way we set this up is that we have two main partitions that are both read-only, and those are what hold your application. Those partitions hold two different versions of your application code, or of your entire operating system, actually, your root file partition. And then there's an application data partition that's read-write. And the idea behind this is you can do firmware updates by alternating which of the root file systems you write to. And if you screw something up, you just fall back to the other one, and everything works great. Can't do that with Debian Linux. So I read all this. I'm like, yeah, this looks pretty cool. It was about a year and a half ago that I was looking at Nerves, maybe 2 years ago now. And I was looking at Elixir around the same time. I'd already played with Erlang, loved Erlang. I was playing with Erlang on my Debian system, and I thought, well, I'll try two new technologies at once. I'll try Elixir on Nerves. What the heck? How bad could it be? So I want to talk about my experience with doing this at Rose Point. And so the first product that we decided to do this with was something called a commercial radar interface. And basically, this is our first product that runs Nerves and Elixir. And it's shipping on the market. It's been shipping for quite a while now. And basically, it's an embedded system built on a hardened board. It's kind of an old school routing board. And it's got two interfaces, and it's got an AMD geode, and It's 500 megahertz CPU and 256 mega RAM, so nothing to write home about. It runs off of compact flash, which is still the industry standard for the hardened, industrial stuff, because you get, that's a whole different discussion, but you get something called SLC flash instead of MLC flash. Those of you embedded systems will know that that's important. So we built this. We wanted it to work. We needed it to work reliably. And basically what this thing does is it interfaces to some commercial radar gear, and it takes scan lines, video scan lines. It actually takes a lot of data, but one of the things it does is it takes video scan lines, and these are not video like left to right. These are video radial. So a video scan line is from the center of the screen out to the edge. So if you've ever seen a radar, that's what a scan line is in a radial scan line in a radar. And these things are all sent as UDP packets, and they're sent as UDP packets really rapidly. They're sent rapidly enough with enough data that if we plug that radar straight into our network, it will take down a number of the nodes on our network. At one point, all our phones stopped working, and we couldn't figure out why, and it's because we had the radar plugged in. So the goal of this device is twofold, but one of it is to isolate that equipment to its own private network and do some compression on that data so that it doesn't end up on the main network that the vessel's dealing with. And it does some other things, including discovery and configuration and some protocol translation. So the first thing we tried, just right out of the box, and this won't compile because I've got dots where there's supposed to be a lot of code. But first thing I tried, I didn't know a lot about Elixir. I kind of had played with GenUDP a little bit. I thought, okay, I'll open a socket, receive some things, get some of these scan lines in and see what happens. Pretty brain dead thing. Wrote this little transform function to do whatever I needed to do. Put it into production, not in production as in shipping, but into my test framework. And this is all in Nerves. Wrote it in Nerves, built it, ran it, and it kind of shocked me because it actually worked. And not only did it worked really well. I had some instrumentation for drop packets, and I had instrumentation for CPU load and memory usage. And after 5 or 10 minutes, I was noticing that I had 214 or 215 megabytes free of my 256 megabytes on this box. And I was using about 10% of my CPU and getting no drop packets at all. And I'm pretty excited about that because they're coming in thousands per second. So, and those of you who know GenUDP will know that this is not the right way to do this, right? Active mode is not necessarily considered the correct way to do this. But hey, it's working, so I left it there, let it go into production, or let it sit on my test bench for a while. And after a couple days, I looked at it, and it's 212 megabytes free and 10% CPU. And so I let it sit for a week, 212 megabytes free, 10% CPU. And during the time, I have connections coming and going. I have all kinds of, this central process is still routing packets, but I have, a Cowboy server that's serving up web requests in this thing. I have all kinds of other stuff, and basically, it's just performing flawlessly. So we let it sit for a month, 212 megabytes free, 10% CPU. At this point, I'm just grinning. I'm thinking, man, I hit the mother lode in technology, because you just don't get that out of Java, right? So I think it was about 2 months, or C, actually, to be honest, from my experience. It's very hard not to have some kind of memory leak in a complex system. So in 2 months, I think it was, when either the power got pulled by a person or the power went out to the building, and I'm honestly not sure which. Either somebody reconfigured it, and then we ended the test. And then I didn't do the best graphs on this, but I'm going to steal a slide from Frank Hunleth here. He actually did a great graph. This is from a project he did, not the project we did. This is a project he did in building a video camera that streams data over HTTP. And you'll see a very similar situation, rock solid stability in terms of memory usage. And I think if he had let that go much longer than 2 hours, like into 2 months, it would have been about the same. To give you an idea how quickly these devices boot, we're in Erlang code or Elixir code in 4 seconds, generally, which is pretty awesome, I think. So we're very excited, but we decided we really needed more, because you can't ship a product just that does that. And So when we started looking at what else we needed to do to make it a real product that we could ship to the market, we realized, well, we really have to support some fairly complex network configurations, like finding DHCP if it's available, but if not, falling back to link local addresses, doing SSDP or MDNS type device discovery, things like that. So we built a whole bunch of stuff, and we needed to put serial numbers in these things, and we needed some configuration data we could put in them that would persist through firmware updates. So we built a little framework on top of Nerves that does most of this and stores data appropriately and manages all the things that you kind of have to do to build an embedded system on top of Nerves. And we were pretty proud of that, pretty excited about it, and talked about releasing it as open source, and eventually did, and I'll talk about that in a second. In the meantime, we built a second device. And when I say we, I worked closely with a colleague named Chris Dutton, and you'll see his name hanging around the Nerves crowd now. Chris Dutton, this was his main project, and he contributed an enormous amount to pushing our framework forward. This is a NEMA protocol gateway. NMEA is a standard for boats. I won't go through all the bullets. This is built on a Beaglebone Black platform instead. We use that as our prototyping platform. When we go into large production, we'll probably do the unification that I described earlier. And it uses CAN bus. And it says C drivers there. Pretty much the only C code we had to write was fixing the CAN bus stack. We really wrote the entire thing in Elixir. And there's a fair bit of Elixir code here. We implemented multiple protocol levels and lots and lots of business logic in Elixir. And having said that, can you guess which of these bullets ended up being the biggest risk in shipping this product? Don't try to design a switching power supply, guys. I don't care how good you are. You got to get an expert for that one. We got killed by the board layout on the switching power supply. So given all of this, I would expect people to be using it. But my experience here is not unusual. Not a single person I've talked to even knows this project exists. And, I don't, okay, great. One, excellent. This is amazing stuff. It really, I believe, could revolutionize embedded system design because it allows you to do such high-level things so easily and with such good recovery from error conditions that you can push the state-of-the-art in embedded systems forward dramatically. So I want to talk about the concept of resistance. And after I did this, I actually called up Frank Hunleth, who started Nerves, and I said, hey, is anybody using this? Am I the only one shipping products? He's like, yeah, you're pretty much the only one. And so I said, well, what's the deal? So we talked about resistance. And I think there's two kinds of resistance that come up to something like this. One is resistance from hobbyists. And these guys are the ones who, they're fine getting their Raspberry Pi and installing Raspbian and dinkering with it and, compiling on the thing and hooking it up to whatever. And that's all they really want to do. And this stuff is too complicated. I don't want to deal with cross-compilation. And plus, I've got a Mac. And who wants to do cross-compilation on a Mac? Because guess what? Buildroot's Linux only. You can't run Buildroot on your Mac. So you want to run on your Mac, you get a virtual machine. And then you got to write your code on your Mac because you don't want to use the editors in Linux, right? Because you like your Sublime or TextMate or whatever, like I do, right? So unless you're an Emacs guy, then you might live with the Linux one. But you don't want to use it through a terminal then, right? So anyway, you write your code in your local file system, then you have to sync your code, and then you have to get your code to build, and then you have to get your images back from the virtual machine, and then debugging becomes weird. It's just a horrible experience for guys with Macs. And from looking around here, I don't think I have to explain why that's important. So that's one set of resistances. It's just too hard, right? But you'd think the professionals wouldn't have that problem. So talking to professionals, they have different resistance to it, right? These guys, they don't care, right? It's what they've always done. They've done it this way. It's C on embedded controllers, and that's what they do, and that's what they know. And the embedded systems crowd, and there certainly are exceptions, but I'm generalizing here, by and large, are stuck in a mental model that is really back in the Sim 1 days. It's, look, we're dealing with the bits and stuff, and we don't want to really deal with Unix because it introduces these uncertainties and latencies, all of which are true, but they don't really want to cross that bridge. And, you know, the weird thing is, the last bullet I've actually heard from a bunch of people where they'll say, we need a language proven to work in the embedded world. And I'm thinking, how ironic to hear that, right? And of course, this is what you say, right? Of course, it was built to run in the embedded world. And, you know, I don't need to repeat any of this. But interestingly, Frank Hunleth, he is a pretty experienced embedded systems developer and hangs around that crowd a lot. And he actually chaired a track at the Embedded Systems Conference in Boston. It happens yearly in Boston this year. So, I mean, he's fairly well known in that crowd. And he presented a proposal for a paper about these issues and talked about how Erlang could radically improve productivity for complex embedded systems because of its concurrency and fault tolerance and the distribution characteristics, right? And they said, well, you know, whoops, that's cool. That all sounds really good, but could you do it in C? And he never got to present that presentation. And the other kind of resistance that you get from the embedded crowd is, hey, look, it seems like I've heard this before somewhere. You know, somebody came and talked about virtual machines, and they talked about remote debugging, and they talked about, you know, having code that would run on multiple platforms before, you know, and it was all focused on embedded. And it didn't work out. And I don't know if I want to try again. One of my coworkers sent me this just yesterday, and I thought, what a perfect slide to put at this point. So I want to talk about where we're going to go with Nerves and how we're going to try to make it a little bit more mass market. When Chris Dutton and I worked on this platform, the library, we realized that you really needed more than just the infrastructure to get going. And so we did build this thing called Cellulose. A few of you may have seen it. Don't go look. We made the classic mistake of open source. We're both relatively new to the open source crowd, so please forgive our mistakes. The classic mistake being we had this relatively tested internal project, and then we tried to snapshot it and release that as open source. It wasn't so good. So we did that. It's out there, and it hasn't been touched for a while. And part of the reason it hasn't been touched for a while is we're frantically trying to get all our code using the public APIs, right? And so we've made a lot of progress on that. We're pretty close. But the other thing that happened, well, let me tell a little bit about these bullets because these are important. So network stuff is pretty obvious, right? You need to be able to be on a network. And device discovery is a little more subtle. Like what happens when you plug one of these things to a network? How do you find it? You're not going to go like into your router and look up this IP address. So there are protocols to do this, but there's not good tooling to use these protocols. And the ability to update firmware and fall back if it fails, actually having some code in the device to do that is pretty important. And then devices need to be able to describe what they do. So it's one thing just to find a device on the network, but if you can't figure out what it is, that isn't particularly helpful. So all of these things kind of play together. I'm not going to go into all the details of them, but I'm going to give a little demo if I have some time left. Let's see. So another thing that happened is a guy named Justin Schneck, who some of you know, sitting over here, called me up a few weeks ago, literally 3 or 4 weeks ago, I think, 4 weeks ago. And just out of the blue, he's like, oh, yeah, I'm headed to Vancouver, and you're in Redmond, and I'll drive down and say hi. I'm like, okay. I didn't really know much about him. So he came down, and we spent the day together. He actually drove several, I think 3 or 4 hours, and took an Uber from the train, or drove the train or something. I don't know what he did. It was a long trip. Anyway, we spent the whole day together talking. We realized we just absolutely agreed on most everything about what Nerves was and why it was cool and where it should go and how it should take over the world of embedded software. And so it started a lot of discussions. I called up Frank. I'm like, Frank, you know, what do you think if we all combine our efforts and try to do something a little more interesting than just having you do this one piece and we do this other piece and Justin wants to come in and help with some pieces? And so we decided we would basically merge our efforts. And so there is now one Nerves effort. And Nerves now, as we define it, is both infrastructure, tooling, and libraries as part of a framework. So we're trying to define not just how you build the software, but we're also trying to define the libraries you'd use, as well as tools that can be used to manage it. The other thing that we're headed toward is we're working on a project called Bakeware. And Bakeware, and I have to give Justin credit for this icon, which I think is the coolest icon I've seen for a while. Bakeware is a tool that lets you build firmware on a server. This is magical because none of you want to go through the pain of trying to do it in a virtual machine or installing a custom version of Linux just to do it. And it really does get you to the point where you could rapidly get from an idea to something that's actually running on one of these devices. So I'm actually going to try to do a couple demos here. We'll see how they go. They're somewhat dependent on internet connectivity. So I'll go for that. Let's see if I can figure out how to get my screen into... Huh, I thought I knew how to get it into not kiosk mode, but I'm not doing so good. Let's try this. Yeah, you know what's? I put it on my menu bar and it disappeared. Is there an icon for it?
No, I don't know. Just Command F1 stops.
Oh, Command F1. Thank you. Well, try that again. Okay. Huh. It's always. I did this in my hotel room this morning, and it worked so well. I really did. Let's see, displays. Well, let's try turning off mirroring. Just. It's set under arrangement. Mirror displays. I want mirroring on. There we go. Okay. Okay, so this is, oh wow, that's a shock. Okay, so this is basically the hello world of the embedded world. It's nothing more than a little function that blinks an LED. And I was going to live code this, but we've got limited time, so I'm starting with a finished file. You get the idea here, right? But what I want to show is this is basically mix new Blinky plus a couple lines changed, right? There's this code. There's mix.exs, which looks pretty stock. Not a lot to it. I've included an LEDs dependency. Not much else. And then I've also included this thing called a bake file. And a bake file is currently our format of saying, what target am I building this for? So in this case, I'm building it for the Raspberry Pi in Elixir. And Nerves RPI Elixir is actually one of the profiles to find in Nerves. If you go look at the Nerves project, they have various profiles that you can pick from. And I give it a product ID and or project ID, and this stuff is a little bit fiddly and not documented well, so pay no attention to the man behind the curtain there, right? So now what I can do is I can simply do bake build firmware in the Blinky directory, and it'll go out to a server. Well, actually, before I do that, let me do the bake clean. So this will remove everything regarding my project directory from the server. So it actually goes out, it does effectively an rsync to the server and brings all my code up, and then compiles completely in the context of the custom tooling environment that's cached on the server. So on the server, it's already got a compiler that's designed to produce code for the Raspberry Pi that's all cached and ready to go. And these little purple arrows, don't worry about them. They don't mean anything. They really don't. So this is basically a stream that's coming back. I'm learning about streams coming back through Elixir, and I do have an issue that I haven't yet figured out how to figure out that things are done. So I'm working on that a little bit. But now, I'll do what's called a pull, and a pull basically pulls in. It's basically syncing in an images directory into my my project. And so this is effectively pulling down all the things that have been built. which is an optional thing because sometimes it builds pretty big things. Currently, a firmware image includes the entire partition that we want to burn onto a flash storage device. So this goes well beyond just the firmware, and I'll show you in a second. This is taking a little longer than I was expecting, actually.
Both the A and the B partitions, or just the one that you're changing?
It unfortunately brings in both, which doesn't need to happen. It really only needs to bring in the firmware file, which is relatively small. It's about 13 or 14 megabytes. Because from that, I could extract it. And I'll actually show you the... so here's, thank goodness, rsync does do compression. So you can see those are pretty big. Get a little easier. Whoop. So you can see 15 megabytes is the firmware I built. Sounds big. It actually could be a lot smaller. We include a lot of board support for in the stock Raspberry Pi, so there are things you can strip out to make it significantly smaller. But this is all of Linux, all of Erlang, all of Elixir, and our app, and all the tooling needed to tie them all together. And so now I'm going to burn that onto an SD card here. Wish me luck. I think it's disk 2. Ah, yeah.
Zero. There goes the Mac.
Yeah, it is disk 2. And I do need sudo. And this will take a little bit. So while that's burning, this is one of the devices that runs our stuff, and I'm going to show a little bit about that in a second. But I welcome you all to come up after and take a look at this stuff.
You open source the CAN bus stuff?
Not yet, but we probably will. Yeah. I don't know if I showed the, did I show the, I showed the factoring, yeah. I showed the factoring in the,
So when you're updating your device remotely, does it replace all the part completely?
no.
Okay, so it just
No.
replaces
The only thing that has to get updated, I'm actually going to do that if I have time here, but I'm done with this, so let's see if we can actually get lights to blink to demonstrate how relatively easy it is to do this. Okay, so when the red light goes out, it starts booting. So there's the start of boot. There you go. That's Elixir code. Thank you. Okay, I'll do one more little bit of a demo to show off the libraries that we're working on. So this is one of our devices. This is our second device that I described that had the interesting work with the power supply. And you can see there's a green light on it. And what I'm going to do, I've got a bunch of different firmware on here, but I have a tool called Cell. And Cell is we call these things, we've used the term Cell to refer to devices that have a grouped functionality that can be discovered, updated, and so forth. And I know I'm almost out of time here, but. So I'm going to do this, and indeed, it just found this device. So I'm on wireless. This thing's on Ethernet. Thank God they're bridged properly, right? And it's running this version of firmware 1.5.0. And you can see we put in tooling for putting serial numbers on and all that kind of stuff. So now I'm going to push some new firmware to it. And this syntax .207 needs to change, but basically we use the last octet of the IPv4 address as a shorthand for referring to the thing. Usually is not ambiguous, but could be, so it needs to change. But so I'm actually going to push some newer firmware. So instead of 1.5.0, I'm going to push 1.5.1. And so let's see if this works. So it's basically doing a HTTP put right now with a bunch of cryptography to ensure that it's actually legit. And if we're lucky, this thing will, once that firmware gets updated, taking longer than expected, actually. I love demos. Well, while I'm doing that, let me go to a different, oh, wait. Update failed. Interesting. Oh, well, maybe I won't get to show this feature off.
There may be some filtering, switching stuff going on.
Yeah. Well, I got a 500, though, and that's not good. That's the first time I've ever had that happen. So I'm actually going to look. This is a piece of JSON being served by this device that shows its current firmware, its branch, its date, the repo where it can get new firmware if it needs to, and the version it's running, which indeed is this. So I'm just looking at this in a web browser. And what I'm trying to do is update it. And interestingly, it didn't work so well. Yeah. Oh, OK. OK, so now it's got, for whatever reason, it worked that time. So you can see it's flashing the firmware right now. And that's basically rewriting the partition table, rebooting. I don't know if you guys can see this. But the light turned red, rebooted. And now it's booting new firmware. It's in Elixir code already. That's the flashing green light means it's acquiring an IP address, and it acquired an IP address again. So I should be able to find it again. And this time, it should be running the new firmware. And indeed, it is. And you'll notice, thank you. You'll notice it says provisional. The provisional basically means we don't trust it. So if I unplug it, I haven't verified that this firmware works. So if I unplug it and plug it back in, it will now go back to its old firmware before I did the update. So we have this idea that we have to manually verify firmware to make sure it actually is good before we commit to using it. And indeed, if I look again now, I'll see that it's got the old firmware again. Well, once it's... Somebody's got a Sonos player that's producing bad SSDP. There we go. So that's the old firmware again. OK, that's it. That's my presentation. I'm happy to answer any questions after. I know I went a little over, but I think we're up against a break. Hope you guys found that interesting. And, oh, most important thing, the URL. Whoops. Nervesproject.org is the URL to go to, and that will redirect anywhere where if we change it later, that'll be the place to go to find it.